everyone. Thank you for joining us in today's webinar. My name is Rakshit Thakur, and I am working as a lecturer in Aeronautical Department, Parul University, in Diploma Studies. Let me tell you over here that Parul University is the leading provider of innovative graduates all over India. Today we are presenting a webinar title, and our title for this today's webinar is Introduction to CFD and its applications. Okay, so it is more about the computational fluid dynamics that you can say, like it is having most of the application in aerodynamics and the aviation as well. And the webinar is presented by Professor Dhruvin Shah sir, and just we'll do a little housekeeping before we get started, that if you have any question during the presentation, please type me to my number. My number is 94264329946. I'll bring them up during the presentation, and we'll also have a time for the question at the end. So now, without further delay, I'll turn the screen or turn the time over to Professor Dhruvin Shah sir, our presenter today in this today's webinar, and he is having very great knowledge and expertise on the subject of CFD. So, sir, it's all about you, sir. Yeah.
Thank you.
Over to you.
Yeah. So, good afternoon, everyone. I hope you all are safe and staying healthy. So, first of all, I would like to thank Manpreet Patel sir, Karnel sir, and Rakshit sir for inviting me for this webinar. Basically, in today's, let me introduce myself. Myself, Dhruvin Shah. I am currently working as an assistant professor in the Aeronautical Engineering Department at Sardar Vallabhbhai Patel Institute of Technology at CIT Nagpur. My qualification is BE in Aeronautical Engineering and MTech in Computational Physics. And today, as Rakshit sir has alluded to, we are going to talk about the introduction to CFD and its applications in not only the aeronautical or aerospace engineering, but in all computer engineering and science. So let me start today's webinar without wasting any time. So I'm presenting my presentation. So then, if you have any questions during the webinar, you can convey it to Rakshit sir, and I will try to answer all your questions.
हेलो ध्रुवीन सर, वच्चे बैकग्राउंड थोड़ोक नॉइस आवे छे. Sir, mic is mute.
So is my PPT visible now?
Yes, sir, it is visible. Yes, sir.
Okay. So our today's topic is CFD, which is broadly known as computational fluid dynamics. And as you are all, most of you are from the diploma engineering, this is going to be the advanced subject that you will come across in your bachelor's or your master's degree. So that is why I have kept this as an introduction and application, and just brief idea about what is CFD and how we can apply it to the various branches of science and engineering. So let me start with the outline of today's presentation. So in today's webinar, we will be discussing about this CFD. But before I come to CFD, I will give you some some brief idea about civil and fluid mechanics, then aerodynamics, and then we will be talking about the fluid dynamics and the computational fluid dynamics, so that we can basically link this topic to the topic that we are going to study, aerodynamics, and we will see how we can solve any fluid dynamics problem using CFD. What is the procedure, and of course applications, and some also interesting applications that basically you will be amazed to know about CFD, right? So now let me start with the basics of fluid and fluid mechanics. So all of you know that every substance in this real world, basically it can exist in three different phases, that is solid, liquid, and gas, right? Now you all are aware with the molecular structure of all these three substances, that is solid, liquid, and gas, right? All three phases. And if you just go into the detail of their molecular structure and their behavior, you will be able to understand that whether it is a liquid or whether it is a gas, they both has capability to deform under the action of any shear stress, right? However small it may be. So even if you have a small shear stress, then whether it is a liquid or whether it is a gas, they will change their shape. They will float. They will flow, right? So that is called the deformation. So it is a property of liquid and gas to undergo deformation or to change their shape under the action of some shear force compared to the solid, whereas solid has the capability to resist the shear stress up to a certain amount, right? So if we talk about, and the science of all these three phases that we are talking about, or science of any substance, it is basically broadly classified or broadly known as basically the continuum mechanics. And if you divide the continuum mechanics, if you classify continuum mechanics based on the behavior of this solid, liquid, and gas under the action of let's say shear stress, right? It will be divided into two parts, that is fluid mechanics and the solid mechanics. Now you have studied, I think, both of this, that is what is fluid mechanics and what is solid mechanics. We are here we will be talking about fluid dynamics, so I am not touching the solid mechanics. You know what is solid mechanics, where you talk about the stresses and the forces, bending moments, that all comes under the solid mechanics. Here we are interested in fluid mechanics. So when it comes to fluid mechanics, first of all, what is fluid? So fluid is any substance which, as I mentioned, which deforms under the action of shear stress. So whenever you are applying some shear stress to liquid or gas, right, they will float, they will change their shape, right? They will flow, right? So that is called basically deformation. So this property of any substance of deforming under the action of shear stress. So these types of are whether it is a liquid or whether it is a gas, they are basically under one title, they are classified as a fluid. And the study of the forces acting on this fluid, it basically, or the science related to the study of these forces on the fluid, it basically known as a fluid mechanics. Now again, further fluid mechanics can be again further classified as fluid statics, fluid kinematics, and fluid dynamics. Now the major difference between static and dynamic is that in fluid statics, your fluid is not moving and your fluid is steady. But whereas if you talk about the fluid dynamics, here we are considering the fluid which is in motion, and also we are considering the forces which are responsible for the fluid to flow, right? Like pressure forces, right? So the major difference between static and dynamic is that in fluid static, your fluid is at rest, it is not moving, whereas in case of a fluid dynamics, your fluid is moving, right? Now the science of moving fluid and the science of the fluid at rest, it is completely different, because when you have a fluid layers which are moving with, let's say, the different velocities, right? They have the capability to produce some friction, some shear stress because of the relative velocity adjacent layers of the fluid, right? And that gives rise to the stresses called shear stress, and these stresses you have to take into the consideration while you are analyzing any fluid dynamics problem. So in fluid static, you can say that my shear stress is zero. In fluid dynamics, you have to include the shear stress as well as the forces which are responsible for the fluid motion, like pressure forces, right? So that is basically called as a fluid dynamics. So once we have understood what is fluid dynamics, we will be now moving towards the CFD. But before that, again, when you have a fluid dynamics, your fluid may be like, maybe you can consider that it may be a water, it may be air. Let's say, for example. So hydrodynamics is basically the dynamics of the fluid flow, which involves the movement of liquids, whereas in aerodynamics we are talking mainly about the movement of the fluid, which is basically nothing but the air. So let's say, for example, if we talk about the example of a moving aircraft, so the airplane moves through the air, or we can say that air is moving over an object like an aircraft, right? So that is basically considered as an aerodynamics. If we talk about the flow through pipe, where the water is moving through the pipe, then that can be the example of hydrodynamics, right? So these are the two sub branches of fluid dynamics, we can say. So now again, we are, as an aeronautical engineer, we are always interested in aerodynamics, right? Once we understand what is aerodynamics, we will be trying to move towards the CFD. And remember that CFD is not only applicable to aerodynamics or hydrodynamics separately; it is applicable to all fluid dynamics problem. So let us understand what is aerodynamics. So you know that what is aerodynamics. Aerodynamics nothing but it is the study of the flow of air through any object or over any object, right? So as I said that as an aeronautical engineer or aerospace engineer, we are interested in the movement of the space vehicle, or movement of aircraft, or movement of helicopter through the air, right? So the study of this airflow over this moving object is basically known as an aerodynamics. Now, what happens? Why we need to study aerodynamics? Why it is important as an aeronautical? Why it is important for you to understand aerodynamics? Because in order to achieve the best possible performance of your design, you need to have the highest amount of lift and the minimum amount of drag. If you talk in basic, right? So in order to maximize the lift and in order to minimize the drag, which is basically directly related to the efficiency, right? So you must have studied that the ratio of lift to drag is nothing but it is known as an aerodynamic efficiency. So you need to maximize the L by D ratio, that is lift to drag ratio, right? So you can do it in two ways. Either you maximize the lift, either you minimize the drag, or either you can do it both simultaneously, that is increasing the lift and minimizing the drag. Now, if you have a design of an airplane, or if you have a design of a space vehicle which is capable of having the maximum lift and the minimum drag, right? Then it is basically directly related to your efficiency as well. So you can also make it more fuel efficient. This kind of design, right? And this can be only studied with the help of the science related to the movement of the air over an object, that is basically known as an aerodynamics, right? So this is the aero. Yes,
Sir, sorry to disturb you over here, but the presentation is on the first slide. You have shared the screen actually. The slides are not moving.
just wait. I have already said. Let me do it again.
Exactly, sir. Now it is visible. Okay.
Can you see the current slide, Introduction to Aerodynamics now?
Yes, sir. Yes, sir.
Okay. Yeah, we were discussing about the importance of aerodynamics. Now, as I said that importance of aerodynamics as an aeronautical engineer or as an aerospace engineer, it is of more focus because we always deal with the objects which are moving through the air, like aircrafts or some spacecraft, right? So we need to make them aerodynamically efficient, and you can make them aerodynamically efficient by having the characteristics like lower the drag and minimum drag and maximizing the lift, because it is known as the aerodynamic efficiency. So how you can basically study this? So let's say if you have designed something, if you have a design of any aircraft in your mind, and if you design that, and if you want to check the aerodynamic performance of this, how you can do that? So one of the answer is CFD, that I will be coming on later in after a few slides. So this is the introduction to aerodynamics. Now I have included some of the slides just to think that you can think of the developments in the design that took place, right? And remember that in those days you did not have that much efficient methods of measuring the performance like CFD. You always have to carry the experiment after manufacturing that particular design, right? Before manufacturing, you cannot predict that in those times people could not do that because they were not having this much of efficient algorithms or efficient methods of having some idea about the performance of a particular vehicle or particular aircraft design without manufacturing. So you can see that in the first slide, on the left slide, you have the very well-known Wright Flyer in 1903, right? The design, and you also will you also agree with me that with time, with the passage of time, your designs are becoming more complex, right? So because of uh, that is because of the these efficient algorithms, like or methods which are used to analyze this kind of designs and to study the aerodynamic designs of certain aircrafts. So yes.
Sir, again, sorry to disturb you, but if you have started that PowerPoint presentation, the slideshow, so because of only that reason only we are having that the previous slide, the slide which you are moving in slideshow presentation, that is not visible actually. We have a present screen presented over here, but that is the actual PowerPoint home,
Okay.
not the slideshow, sir. Yes, now it is fine. Yes, sir. So over here, if you can change the various slides, so it can
Yeah.
easily visible. Sir.
Okay.
Yes, thank you, sir.
Uh,
Sorry to
so
disturb you, sir.
This is what the development that took place over the period of time in the various designs of the aircraft. So in the first figure, you see the well-known Wright Flyer aircraft. In the right figure, you see that Supermarine S6B aircraft, which is capable of taking off and landing from the water in 1931. If I give you some more examples, you can see the first supersonic aircraft, which is basically Bell XS-1, right? And you can see the design of the nose, that it basically designed specifically to deal with the supersonic speeds, right? And in the right side again, you see X-15 aircraft, which is the first hypersonic aircraft. So these are the various developments that took place over the period of time. So what I just want you to said this different designs of the aircraft over the period of time is to ask
question to yourself that how designs are being were getting modified in those days, right? So because people used to manufacture the whole aircraft. They used to take the test flight, and if the design fails, they used to modify it, again manufacture it, again modifying it, again manufacture it, and again modifying it. So remember that first they had to manufacture the design, and they have to taste it physically. They did not, and basically this was very time consuming, and as well as the cost consuming as well, right? So what I mean to I want to draw your attention towards the efficiency that we have with the help of the technique, or I would say the research tool, which is known as a CFD. So how your CFD has changed the entire methodology of saving the time and the saving the cost. So that is why I just put it these three slides, that CFD would help you to avoid the physical testing without any prior expected outcomes, right? So you will have expected outcomes, and then you can basically go for the manufacturing. So this saves your lot of time and cost. So coming back to the aerodynamics part, as I already mentioned, that we want to analyze the moving object through the air in terms of the performance parameters like lift, drag, thrust, etc. Right? So and this gives us the some idea about our probable design, right? And if you want to then modify your design, you can basically modify it accordingly, right? So this is about aerodynamics. So what you can analyze with the help of aerodynamics, or what you can get by aerodynamics, you can get the pressure distribution over an object. From the pressure distribution, you can calculate the lift, you can calculate the drag, and with the help of lift and drag, you can further analyze the various performance parameter for that particular design, right? So it gives you the information in terms of the forces. It gives you the like forces like lift and drag from the pressure distribution, and this is going to be, and we know the importance of lift and drag in the performance of any vehicle or any aircraft, right? So this information about the forces and moment, it plays a vital role in analyzing the airplane performance, and such aerodynamics problem can be solved using the fluid dynamics, because air is also a fluid, right? So although it is an aerodynamics, but aerodynamics is a branch of fluid dynamics. You also have the hydrodynamics as well, right? So aerodynamics is the one of the small part of fluid dynamics. Now, how we can basically study these problems, right? Our aerodynamics problem. So first of all, for that you need to understand that what are the physical principles are involved in any fluid dynamics problem, right? So whenever you have a fluid is in motion, you have certain laws of science which are used to study the fluid dynamics. So there are if I say there are three principles on which the whole fluid dynamics is based, right? So remember, we are still talking about the fluid dynamics. We have not yet introduced to the I have not introduced you to the CFD. We are still now on the fluid dynamics. So, and whenever your fluid is in motion, it is considered as a fluid dynamics problem, whether it is aerodynamics or whether it is a hydrodynamics. Now, to study the fluid dynamics, you need to first understand the fundamentals of fluid dynamics. The whole base of fluid dynamics lies in these three physical laws. And which are these three laws? So first is the conservation of mass, right? So we know that basically the conservation of mass is nothing but whatever mass is inside the container, the same mass is coming out of the container. That is called the conservation of mass.
Second principle is Van Newton's second law, that is basically says that F is equal to ma, which is basically the force is equal to mass into acceleration. And the third principle, that is the conservation of energy, and we know that energy can neither be created nor be destroyed, it can only be converted from the one form to the another form. So these are the three laws.
Sir, yes, actually background noise is, just coming. Sir, still a lot of background noise is there.
I think it is not from my end.
Okay. Yeah, sure, sir. Can you make one thing? Like just once you mute and again unmute that, it will be good. Yeah, fine, sir.
So these are the three basic principles of around and I can say that this is the whole base of fluid dynamics, whether it is aerodynamics, whether it is hydrodynamics, life is only that is conservation of mass, the second law of motion, and the third is conservation of energy. What does mass conservation mean? The mass conservation is simple language means that if you have a control problem and the material of mass of fluid is coming into the control value, the same amount of mass out of the second is Newton's second law. Newton's second law says that F is equal to ma, and the third one is conservation of energy. That is, you cannot create energy or you cannot store the energy if you can convert it from the one point to another. So these are the three basic laws, physical laws of dynamics. And now these laws will be applied to the particular problem and which is resulted into a corresponding equation. So let's say if I apply the conservation of mass, if I convert this principle mass conservation to the control value, and if I get this principle converted into the mathematical form, it will show the continuity. Remember, applying the mass conservation on the given control volume, and the mathematical form of the state will be known as the continuity. Similarly, if you apply the Newton's second law to the control volume, then the mathematical form of the second law will be known as the momentum, and conservation of energy is known as the energy. So these principles, when they are applied to the particular given control volume or given problem, it will be converted into the mathematical form. So if I represent this physical form in terms of the mathematical form, they will be given as the continuity equation. So now you want to highlight that solving two dynamic problem means solving this equation statement. That is continuity, motion, and energy. So when you solve this equation, you get some of the basic field parameters like density, x velocity, that is velocity in x direction, velocity in y direction, velocity in z direction. You get pressure, you get temperature. So what you are getting density, you are getting velocity, you are getting pressure, you are getting temperature. So these are the basic fluid parameters, basic fluid properties that you obtain over the entire domain by applying this, by solving this mathematical equation, that is possibility of controlling energy. So now if I say that solving fluid dynamics problem means the solving of a solution of this method, that is continuity, motion, and energy. But before this, let me explain the possibility by which we can solve any fluid dynamics problem. So before coming to CFD also, I would with the help of some pen and paper kind of and we get the exact solutions of this equation. So like we can say that if we have let's say the 3x plus 3y equals to 3, and if you know the value of y, right, you can get the value of x. It is very simple, right? And we get the exact value, not the approximation. Right? So solution of mathematical equation, that is maybe the differential form or integral form or any other form, right? It is basically used with the same parameter, that is density, pressure, temperature, velocity, etc. Right? So these analytical solutions basically is the exact solutions of this mathematical equation. Remember the word exact. You are getting the exact solutions of this equation. But there is some problem with the analytical solution. So this is the most efficient method of solving fluid dynamics problem. That is analytical. But remember that most of the fluid dynamics problems are complex in nature, and that is why if you represent these problems in terms of the mathematical equations, you can tell that is continuously molecular energy. These equations are aimed to be the complex non-linear equations. This is not possible to obtain in most of the problems. It is not possible to solve them analytically. Right? So, like for simple problems, you can get the analytical solution. Like you can say, for example, pipe. Right? So, let us consider the there is a pipe in which let's say water is flowing. So this is a simple problem. Any other problem like flow or a flat plate. So this is there is a flat plate and the fluid is flowing over this flat plate. So these are basically the simple problems, and for simple problems, if you represent these problems in terms of mathematical equations, the equations also will be simple, not the complex and non-linear. And so it is possible to solve them analytically, but most of the fluid dynamic problems result into a complex non-linear set of equations, and that is why the solution of the analytical solution of most of the fluid dynamic problems is either it is, you can say that it is very difficult or it is next to impossible, right? So that is why this method is not as popular for the solution of the fluid dynamics. Of course, for simple solutions, for simple problems, your analytical solutions are available. As I say that you can refer to any fluid dynamics or any fluid dynamics, you will get the solution of flow or flat plate or solution of flow pipe. So which are obtained analytical, right? But as I said that for most of the real problems, this is a complex set of equations, and that is not possible. Right? So for a second.
Wait, guys. Sir will be back in few minutes. Please wait over here.
अक्षय
Yes, sir. Yes, sir.
हाँ अभी कुछ कम हुआ लगता है देखो.
Yes, sir. It has been
so
reduced now.
I think it was from the fan.
Okay. Fine, sir.
Yeah.
Okay, sir.
Yeah. So the problem with the analytical method or analytical approach is that you cannot solve most of the fluid dynamics problem analytically, and that is why you must look for the alternative approaches, right? So what are the advantages of analytical? So as I said, this is the most efficient solution because there is no chance of any error, and you are getting the exact solution of that particular problem. What are the disadvantages? So as I mentioned that it is only applicable to simple geometry like a flat plate or a closed
or any complex domain. You cannot get the analytical solution because of the complexity which is involved in the non-linearity in the equation. So what is the another approach? So let me talk about the another approach, which is experimental approach. And as if I say this experimental approach, it has to be there every time. It has to be there because it is basically in experimental approach. What we are doing is that whatever design or whatever object that we want to analyze, whatever geometry that we want to analyze, right? We make a prototype of that, right? It is basically a small scale model, right? And that prototype will be tested in a wind tunnel, right? And the flow properties like pressure, temperature, velocity will be obtained through the set of experiments, right? So the experimental method is carry out the experiment on the small scale model because we cannot have the full scale model of the aircraft. So what we do is that we basically convert the prototype of a full scale model and we test it in a wind tunnel and we carry out experiment and we get the values of different flow properties like density, temperature, velocity, pressure, etc. Now, what are the advantages of experimental method? So it basically replicates the exact physics without any approximation. So remember that whenever you are carrying out experiment, right? We try to generate the same environment like it is going to be in the real life, and then we want to then we basically analyze that particular problem. We carry out the experiment and we try to get the result in terms of the flow property. So this is the advantage of experimental, that it replicates the exact physics of the system, right? What are the disadvantages? I would not say the disadvantages, but because experimental is very much required, right? So without experiments, also you cannot go further. So you cannot completely avoid the experiments, but and that is why I would not say that we have a disadvantages, but we have some tough situations or say some challenges during the experiment. So first of all, it is expensive, right? So the cost of experiment is very high. So just for an example, let's say if you want to if you want to analyze the flow over an aircraft. So first of all, you have to generate a prototype of that particular aircraft. You have to put it in a wind tunnel. You carry out the test. You carry out the experiment. You get the properties. Now this is only for one design. And if your results are not as per your expectation, you need to again modify your model. So again, it will involve some cost. Also, you require some skilled person to carry out the experiment. So you have to create a whole experimental infrastructure, right? So it makes the cost of this experimental approach will be more. So that is why it is expensive. Second is time consuming. So as I mentioned that let's say, for example, if I want to test the model at 10 different velocities. So every time I have to change the velocity and I have to carry out the test. And let's say if I also want to taste the different span of wings, right? So different wing span I want to check. So every time I have to manufacture the wing with the different wing span, so it also consumes a lot of time. Third one is that as I mentioned that we require very large experimental facility. Again, that this is how the simple parameter element. Right? So let's say if I at some particular velocity, if I want to check, and I can only get then it is I want to use for the other velocity. Single parameter element be obtained. There is a function or a set of functions which are conducting the experiment. So some human errors are also involved, right? And the risk of life is also involved. So let's say if you want to you are doing some experiment with with some explosive tools, right? Let's say if you are working in a production lab and you are analyzing some problems related to the tool. So that makes it that's actually a problem even in India only. If you have heard about the shooting in some IIT, there is basically particularly visited experimental performance while taking this experimental performance of certain problems. It's basically on fire and the problem was of the IIT. The same time there was and that's what about the IIT had this problem of this matter. So there is a risk of life is also involved here. Look at the actual experiment. And the last one is that difficult so whenever you have created the safety and accuracy, you have to bring your objective at state special environment. You cannot state the state special indication somewhere at right. So that is the problem. So this is the another approach. But I would not completely ignore this experimental. I will keep the experimental. I will give importance to the experimental approach. Right? So you carry out experiment when it is required, at least to have some baseline performance idea, and then for more modifications, for more number of cases, like for different velocity systems, that you can basically look for another approach. So now I'm coming back to the theory. So the third approach is the empirical approach. What is theory? So the principle of theory is to create a computational fluid dynamics. So it is a fluid dynamics, but it is a computational fluid dynamics. So fluid dynamics problems are solved here with the help of some computational power. And I say computational power is basically means that you have a computer program, right? So computer program is used to solve the fluid flow of fluid flow and heat transfer related problems. So that is what is any fluid dynamics problem involving the fluid flow and the heat transfer with the help of computer program is known as fluid. Right? So it is basically you can say that it is a technique for future research. So CFD is a tool which is used for the research of CFD is a technique which is used to solve the fluid dynamics problem. Now, why we are discussing about numerical approach of CFD? It is simple. It can basically reduce the experimental cost and without consuming more time, we can do the experimental approach. Right? So, in CFD, we are also solving the set of equations that we discussed with the analytical approach. That is continuity equation, numerical equation, and analytical equation. But here, in order to solve this complex and non-linear equation, we cannot we cannot solve analytically with the help of 10 and 8 or 2. What we can do is that we use the computer program which is designed with the help of some numerical methods or algorithms in that, and we can use that computer program to solve this type of equation, which is basically experiment, reducing the experimental cost to save your time, right? And you are getting some approximation. So remember that if I ask with respect to natural set, RCFD results, natural set activity, which is no, right? So the results of activity are more 100% accurate or 100% reliable, and that is why I say that I cannot deny the experimental approach, but you can carry out both simultaneously sometimes. Right? So every time you don't need to conduct an experiment, and you have a certain idea about that how my concept is going to behave, right? At some particular place. So I have some baseline data, I will directly take that place. And once I know that my PhD results are are speed and their accessibility matching with the experimental. The next time when I have to do it for the same product or some other product, right? So I will avoid the experimental approach and I can only go with CFD. So CFD is a technique, it is a research tool which are used to solve whether it's the equation, thermal equation, the continuation, momentum and energy equation. And these equations are basically used, they are basically in form of a partial differential form or integral. Now remember that partial differential form and integral form of equations are basically non-convertible form. It is not like 3x plus 2y is equal to 5 by 6, but this is an algebraic equation. You know the values of x, you can get the values of y or vice versa, right? But here, your equations in CFD of fluid dynamics, they are either in the partial differential form, like dv by dx plus dv by dy is equal to 0, or either it is an integral form. So these both forms are basically non-solvable form. You cannot simply solve them like you do with the algebraic equation. Right? So you need to discretize these forms of equation. Now what do you mean by discretization? Discretization means that the breaking of equation into a small number of parts. So when I have the whole equation in the partial differential form, I will convert again into an algebraic form of equation by applying so we can have discretization method. So the discretization means that process of breaking up the whole domain into a number of small domains. So whatever domain I have, like let's say I'm talking about simple air flow, right? So if I want to analyze the flow over an air flow, I will break up the whole domain of the air flow into a number of small parts, and then I will apply the discretization technique. So what are the discretization techniques? So there are three basic discretization techniques. That is basically known as the finite difference method, finite volume method, and finite element method. So these are the process of converting the non-solvable form of equations from the partial differential form or the integral form into an algebraic form. Right? So these are the three methods and the equations which will be result or convert the equation into an algebraic form, and then you can basically solve that algebraic form, because algebraic form is always easy to solve, right? Now coming back to the advantages of CFD compared to the analytical, or mostly compared to the experimental approach, because analytical is out of the way in the complex problem, because you cannot have the analytical solution. Otherwise analytical solutions are the exact solution, but it is not possible in most of the real life problems, right? So the advantages of CFD compared to experimental approach is that CFD is cheap. Why it is cheap? Because CFD is simply a computer program. So what I need is, I need a good efficient computer maybe with some high configuration, like a RAM and hard disk and everything, right? So it basically simple a computer. You require a CFD computer program, so that is a software, right? So CFD, there are CFD softwares like ANSYS or Star CCM or Flow 3D. So there are various CFD computer programs are available in the market right now, in commercial market, but the most commonly used computational fluid dynamics program is basically the one which is known as an ANSYS, right? So ANSYS is a company which has its own product there are various products in the ANSYS itself. So ANSYS is a company and it's used in the computer program, which is one of the most commonly and the widely used computer program right now all over the globe. Right? So coming back to the why it is cheap, so you require simply a laptop or a desktop, you require a computer program or a CFD software, and you require a person who knows fluid mechanics, who knows the fluid dynamics, and who knows how to so these are the only basic requirements in CFD, and that is why it is cheap for
advantage is that it gives you a faster solution compared to the experimental approach, because time taken is very less. In case of a computer program, you can run the problem, or you can keep the you perform the various steps, and you keep your laptop on for the over the night, and morning when you see you have a solution, right? So it does not involve extra time also. No life risk involved, because it is just a computer. So there is no risk of life is involved, and easily portable. You can take your computer anywhere, right? You can take it to the office. You can perform there, and you can come back to your home. Again, you can perform. So basically, it is not like the experimental possibilities which cannot be reported, right? So it is easily portable. So, as I mentioned, that all three approaches will go in hand in hand, right? So you cannot deny anything. So basically, you have the experimental tool dynamics, you have the analytical tool dynamics, and you have the computational tool dynamics, and they all are interrelated, right? This is the same thing that in terms of cost, time, scale, information, repeatability, and the shape. So from all aspects, if you see the CFD, it is cheaper, it consumes less time. You can solve any scale of problem, so you can make a full scale model of the aircraft, unlike the experimental approach. You can get the information at all the points on the aircraft. It is not like experimental approach that in experimental approach, wherever you have provided the cost to measure the pressure, so it will measure the pressure at that particular point as only. But here you will get the pressure at each and every point. Just for an example, right? You can repeat whatever times you want to repeat, right? In case of an experiment, it will involve extra cost. In case of safety, as I said, that there is no likely to know, so it is completely safe compared to the experimental. So what we have in CFD is to see that first we need to define the problem. Right? So let's say if I want to analyze the flow over an aircraft unit, right? So this is the problem. So you need to have the physics of the problem. That how your when it is made up of an asphalt shape, so it is very easy to predict that it is going to have a higher pressure on the bottom side. It is going to generate a lower pressure on the top side. It will have some vortices at the wing tips. So this is some information about the problem that we already know, right? So defining the problem, that what kind of problem you want to solve. So let's say I want to solve I want to simulate the flow over this particular model of a wing at, let's say, 0.3 Mach, right? So this is my and you want to obtain the lift, drag at different angles of attack, and then you want to plot CL alpha curve, you want to plot CD alpha curve, and you want to plot, let's say, the CL versus CD curve, right? So this is the problem definition. Once you have understood the problem definition, then the second step that comes is basically the to write the Navier-Stokes equation. Not actually write the Navier-Stokes equation. Navier-Stokes equations are inbuilt in your software, but you have to define that whether you have to apply the mathematics, or say you have to apply the principle of physical laws that we have discussed, that is conservation of mass, momentum, and energy, to your particular problem. So it will be resulted into a mathematical form of equations, which are basically known as a Navier-Stokes equation. Then you have to, as I mentioned, that these are the in terms of the partial differential form, so you need to discretize them. Once you have discretized them, then you have a algebraic equation, and then you have to solve these algebraic equations with the help of the numerical methods. So there are various numerical methods for different types of fluid flow, right? Which is also inbuilt in your CFD problem. And then you have to choose the appropriate method. You have to apply the boundary conditions, and then you have to finally get the results. Once you get the results, you have to analyze that results, and you have to make some comparisons, right? So this all is everything is there. So there are two problems, or say there are two sides of this. One is the theoretical side of CFD, another is the experimental that we actually do, right? So as I mentioned, that once you have defined the problem, then you have to apply the mathematical principles to your domain, which will result in the set of equations that is continuity, momentum, energy equation. You need to discretize these equations, right? And then you have a discretized form of equation. And similarly, you have to discretize your geometry as well, right? So the discretization of geometry, it is basically known as a grid. So basically, you have to divide the whole geometry into a number of small parts, that is called as a grid, right? And then you have to use the computer program that is basically known as a CFD software, or the numerical methods which are involved in that particular software, and you have to apply that numerical method for the solution of this, and then you have to solve this. And once you get the simulation results, you can basically do the comparison with the experimental results as well, or you can compare it with the other software results as well, and you can compare it within the for the same problem. You can compare the different. Am I audible?
Yes, sir, you are audible.
Yeah. So you can compare it with the different cases also, right? So this is the whole CFD process. Now, as I said that these are the discretization methods. So commonly used discretization methods are finite difference method, element method, and volume method, right? So the most commonly used methods of discretization nowadays, it is finite volume method, right? So this is just for your understanding. It is used to discretize the partial differential form or the integral form of the equation and convert them into an algebraic form. Now, coming back to the discretization again. So as I said that the overall idea in discretization is to divide the whole geometry into number of small parts. So discretization of mathematical equations is done with the help of the finite difference method, finite volume method, or finite element method, and simultaneously, while actually doing CFD analysis for practically, then you have to discretize your domain as well, right? So your problem or your domain is what? Actually, it is airfoil. So you have to also divide the whole domain or whole airfoil into a number of small parts, right? And then you have to apply those discretized equations to each of the small domain of the airfoil, and then you have to solve for each small domain, and then you will have a set of equations, and then those set of equations you have to solve with the help of and you can get the solution in all local parts, right? So if you want to solve the flow over the entire domain, you have to solve the you have to get the solution for the small domain, right? And you have to find the solution of small domain, it will give the solution in the entire domain, right? So this is how the CFD works. And coming back to the equation, so as I said that CFD has got variety of but remember that it is endless. Whenever there is a fluid which is in motion, there is CFD, right? So let's say electronics. So I have only included few of the applications here. So let's say if you have the electronics branch, so you have a chip, right? Small electronic chips you have. So so the cooling of that chip, because if the temperatures are not maintained, that chip will be useless, right? So you need to maintain the chips in your computer, in your laptop, or any electronics, right? So for the maintaining the enough temperature of the chip, you can solve this problem using CFD. You can take the turbo machinery, like if you take the aircraft engine, right? Or maybe the pump, maybe any machine which has rotating machines, like you have a compressor, you have a turbine, you have a nozzle, you have a diffuser, you have a fan, right? So everywhere there is a flow of air or flow of liquid there which is in motion. You can use any turbo machinery problem using CFD, right? So the best example is the aircraft engine, right? The third one is, let's say that if you take the civil engineering. So let's say if you are constructing large tall buildings, so you have to see that how it is for heat, especially the HVAC, right? The air conditioning and the ventilation, you need CFD so that you can have a good site. Also, what you can analyze is that if you put the different buildings at different angles over with each other, or how far you have to put different buildings so that the flow of one building will not affect the other building, right? So that also can be done with the help of CFD. Automotive aerospace is the most common application of CFD. So aerodynamic design of vehicles, right? That is automobile vehicles as well as the aerospace vehicle. That is whether it is a car, whether it is a two-wheeler, whether it is a cycle, whether it is a aircraft, whether it is a flow behavior biomedical engineering. We have in our body there is a flow of a blood, right, which is continuously flowing. So you can basically analyze that also with the help of like blood flow through the arteries can be studied with the help of CFD. Then sports, you can take the performance of athletes, right? I mean, especially the various positions during the running competition can be an applications of CFD, right? So why Trent Bolt, sorry, why what I mean to say is that different positions of the runners can be cause of their performance, right? So this what position you should take while running, that also can be decided with the help of CFD, right? You can take the similarly in swimming also, what position you should take while swimming in order to minimize the drag and increase your speed. That also can be studied with the help of CFD. You can take the swing of a cricket ball, right? So that also can be studied with the help of CFD. Similarly, for golf ball also you can do the CFD, right? And you can have the performance. So if I give you the pictorial view of applications of CFD, so you can see that automobile flow over a car, then aerospace flow over an aircraft. You have a waterfall, right? So what pressure it will generate, what kinetic energy it will generate. Waterfall, for different width of waterfall, you can analyze the ventilation in your car, right? So it is one of the major applications of CFD, right? So airflow and ventilation in your car. So when I have to put the air vents, how many air vents I can put in a car for the better in terms of the air distribution through air conditioning. That also can be an application of CFD. In biomedical, blood flowing in the arteries and reaches to the heart, that also is an application of CFD. Different swimming positions, that is also, or postures can be studied with the help of CFD. And right now I'm talking about some interesting applications of some CFD, which you find, I mean, you will be amazed to know that this can be done with the help of CFD. That is the conventional swing and the reverse swing of the cricket ball, right? So just if I spend 2 minutes on this, you can see that on the left hand side figure you have the conventional outswing that occurs, right? So I hope all of you are aware with the swing that occurs in a cricket match. So with this season ball of which is used in cricket, it is capable of producing two types of swing. Normally, that is a conventional swing and the reverse swing, right? So the conventional swing occurs normally when your ball is new, right? So when your ball is new, the whole ball is having a sign everywhere. I mean, on both the sides of the threads, right? So normally the bowlers put it into the airflow, right, at some angle. So you can see that it is slightly inclined to the airflow, right? So the air is flowing coming from the front, and the bowler put the seam position at some angle, right? And that is why the more number of threads will be coming on the left half of the airflow compared to the right side. So you can see that on the right side you have a more shiny part compared to the left side. So the left half will be a rougher part compared to the so you have one side, right side, as a smooth part, and the left side, which is basically a rough side of the ball, right? And when you have a rough side of the ball, it generates a turbulent boundary layer, whereas if you have a smoother side of the ball, it generates a laminar boundary layer. Now remember that the flow separation that you must have studied over an airfoil or over the aircraft wing, that also occurs similar on the cricket ball as well. So the flow separation occurs on the laminar side is basically it occurs at some later part compared to the turbulent side, and that is why you have a pressure distribution which basically causes the ball to move to the left, that is away from the batsman, right? So that is the conventional swing that occurs when the ball is new. And when the ball gets old, normally both sides of the whole ball gets old, but players are keep on running the ball to maintain the one side as or say maintain the sign of the one side, so that they can get some of the swing from the old ball as well. So normally the swing that is more popular with the old ball is basically known as a reverse swing, right? So with the same orientation of the ball, like we did it in case of the conventional swing, this will produce a swing in the opposite side. So this will produce a differential force in the opposite side, which will come towards the batsman, right? So going inside, and this occurs because both sides now are sides, but one is having a slightly smoother side compared to the other side, right? So this again generates, so both sides now the layers of the air will be a turbulent boundary layer, but one is having a more turbulent in nature compared to the other, right? You can see that on smoother side also you have it is not a smooth side, it is a smoother side, right? So it is also rough, but it is compared to other side it is less rough, right? So you have again turbulent boundary layer, and you have a more turbulent boundary layer. So again it will generate a difference, and it will cause the ball to move towards the batsman. That is called the reverse swing, right? So you can see that you can analyze this with the help of CFD. And just to let you know that some of my students in 2015 have performed this analysis as their part of their project, and they published a paper as well by doing the CFD analysis of the reverse swing of a cricket ball, right, at various by changing the various parameters. So this is one of the interesting applications of CFD. Another interesting applications for CFD is the different cycling position. So you can see that on the left hand side, you see there is a cyclist, which is and said the position of the cyclist is different in each of the three situation, right? So you can see the bend. In the first case it is less bent. In second case it is more, and in third it is highest. So just to study the airflow behavior of the arrow in three different positions, and you can see that the velocity distribution is already done in for all these three cases. And at the end you can calculate the drag, and you can choose the position which basically has the minimum drag, right? So these are the two applications which I have involved. I have taken this just to show you the wide applicability of the CFD. In aerospace, there are of course there are highest applications of CFD, but other than this is also an aerodynamics only, right? The flow of air through the ball or through the cyclist, that is also an applications of CFD. Yeah. So now I hope I have covered some of the introduction and applications of CFD. Now I would happy to answer your questions if you have any doubt in this. So if you have any questions, you can answer.
Awesome, sir. What an application of this CFD. I now most of the students have understand scenario in test match, like why the cricketers are always rubbing their rave ball every time with their clothes. So now everyone has cleared the concept, and it was an awesome session, sir. And one of the questions from the most of the audience is which is a good platform to learn CFD, or is there any book that they can refer after diploma so that they can clear the more detailed concept about the CFD?
Yeah. So to answer this question, first of all, I would prefer that you require to learn CFD in a proper manner. You need to have a certain basic theoretical ideas about this. So you must be clear about the aerodynamics concept as well as the fluid dynamics concept, and for that you have to learn you have to clear your fluid dynamics concept theoretically correct before performing it to the practical. Before implementing the practically. So for that, one can learn the CFD. I'm talking about the theoretical CFD by referring book that is Introduction to CFD and its Applications by J.D. Anderson. This is one of the basic book of CFD, and it is given in a very simple language. So I think for diploma students also it would be good to start with.
Thank you very much, sir, for your answer. And if you now allow me to present my screen, so you need to stop the presentation over here.
Yeah.
So I want to share one moment from the Para University side, and as a token of appreciation, I would like to share this certificate for the appreciation for this effort for organizing and having this awesome subject webinar on this particular title, that is Introduction to CFD and Applications. Thank you, sir. Thank you very much for coming over here and giving our students about the idea of CFD and the introduction of CFD. They have learned a very lot, and it was a great session. So thank you everyone over here. We appreciate you being here, and thank you very much, sir, for sparing your valuable time and this awesome knowledge.
Thank you, Rakshit, and again I thank everyone who is involved in organizing this webinar, including the head of the department, Ankit sir, Karnel sir, and yourself. And I'm thankful to Parul University for providing this opportunity to interact with the young mind. And just as a final remark, I would happy to share my knowledge on CFD or some other subjects with teachers, your students, so in each and every possible way. So I can guide them for their project. I can help them in any possible way. Thank you.
Thank you, sir. Thank you very much for that support. And we will be having our next webinar scheduled in next week. So please join us for the further interesting subject. And the time and the date will be updated soon. So thanks again for joining us today, and we will see you the next time. Thank you, Dhruvin sir. Thank you very much.
Thank you
for the interesting subject webinar. Thank you.